So one of the reasons why we're using formal charge is we can justify which structure is more stable. All three of these structures are possible because they follow the octet rule and they are using the correct number of valence electrons. So if I asked you to draw this Lewis structure, you might come up with all three of these, which is totally fine. This is what resonance is. The idea of resonance is where all three of these structures exist and the compound actually switches between these possible structures very, very, very fast. And in some cases, it's a blend between these where we're going to get, when we get into hybridization, we get to explain that a little bit better, how these bonds blend between a single, double, or triple. But usually resonance has to do with where do the double bonds go? Where do the triple bonds go? Are there more than one option? You're not going to see resonance if they're all single bonds. It has to be some sort of double bond that can be here or here. And so you can draw it in multiple ways. There's a very valid question that could be asked on assessments that says, draw all possible resonance structures. Now, when we're looking at these, based on our determination of formal charge, we can assign formal charges and have a level or a way to analyze which structure is more stable. When we talked about Wednesday, one of the things we said is a structure is more stable when the formal charges are minimized or the closest to zero. So let's go through and assign formal charges to each of these. So take an opportunity to draw each of these structures down on your notes. And we're going to go and assign formal charges to all of these. In fact, why don't you do that yourself? Compound A, B, and C, resonance structure A, B, and C. Assign formal charges to all of the elements in all three of these structures. When you're looking at justifying which Lewis structure is more stable or exists for longer, the less stable one will exist. The electrons are always moving around in constant flux. But the more stable ones could exist for a longer period of time, and the less ones will exist for a shorter period of time. That's one way to consider how stability is shown in the real world. Like how does it measured? So the more stable ones are assumed to have the formal charges closer to zero. And then if there's a substance or if there's an atom with a negative formal charge, those prefer to be on the more electronegative element. That's one reason for electronegativity or using electronegativity. It talks about atoms that are more stable with a negative conformation or more negative state than its neutral state. So in this case, oxygen is the most electronegative element of these three. So when there's a negative formal charge, it prefers to be on oxygen for longer. So if I go through and identify for B, that looks like this is going to be a -1 nitrogen and a 0 oxygen. And then we have a 0 nitrogen and a -1 oxygen. Where in all cases, carbon has a formal charge of 0. Carbon is nice and usually going to have 4 bonds coming off of it, whether it's some combination of single, double, or triple. We're rarely going to see a formal charge on carbon because carbon is typically a central atom. It's going to have its octet through bonding. So of these three, A, B, or C, type in chat, which one do you think is most stable or exists longer of the three? Nice. So we're just applying some rule set to some relatively simple rules or ways to analyze Lewis structures. And as long as you know what those rules are and you practice analyzing structures, I think that the steps we're taking are relatively straightforward. And everyone in chat that's typing is saying C. C does exist longer than the other ones. All three of these are possible. They do exist at some point, and that's measurable because the bond lengths are changing strength and size. Mainly, the difference between the single, double, and triple bonds is the length. So we can see these carbon and oxygen bonds oscillate back and forth between a shorter conformation and a longer conformation. That's assumed to be the moments when there's more electrons being shared between those atoms and then less electrons being shared between those atoms. And so we can measure it based on bond length. Good. So if you had to choose one of these to be the most correct structure, I would go with C. If that was kind of a most stable or most preferred structure, then I would select C. Okay. Thanks for doing that with me. Here's just and when you go into the PowerPoint, it's kind of says exactly what we said. Some ones that I want us to try. These ones are actually on our list. So these are ones that I'm going to talk about when we're done, but I'm going to send us to groups, and let's go back to our list of our A through K, I believe, whatever the number was. And I want you to, now that you have an answer key for that, I'm going to put that image on Google Classroom if you need to look at that key of Lewis structures. But I want you to go back through and identify any formal charges that are not zero. If there's zero, you don't have to write it. Just formal charges that are not zero. We'll speed it up a little bit. Let me go back to that list to show you what I'm talking about. And I'm going to send you to groups to try this together. So however you want to do it as far as trying it on your own and then comparing. That's this one. So just go back to your list, and now you're going to add on to the structures you've already drawn non-zero formal charges. Some of them, they'll all be zeros, and that's fine. But a few of them are going to have non-zero formal charges. So you're going to try and find those and write down the formal charges. And any that have zero formal charges, just leave them blank. That's fine. So I'm going to send you to groups. It'll probably take you 5 minutes, maybe a little bit longer, to identify the ones that have formal charges and write them down. And then again, if there's no formal charges, just leave them blank. And we'll look at a couple that are a little tricky. And I'll see you back in 5 to 10 minutes. I'll put those back up because I can see them all. -1, +1, +1, -1, +1, -1. So as you can see, it's not as common, but it is going to give us some extra level of justification when we are trying to determine which Lewis structure is most correct, mainly when there's double bonds and triple bonds. Where are the double bonds and triple bonds most likely to be? With N2O in particular, there was a few different structures that I proposed to as which one is more correct. And I want to do that really quick, and we'll take a brief intermission. The nitrous oxide one, we'll do ozone later. With nitrous oxide, we have the triple bond format, we have the 2 double bond format, or you can have the triple bond to the oxygen format. And so what we are able to do is use formal charges to justify which structure is the most stable. If we were to just draw one Lewis structure, which would be the best one? And so when I'm going ahead and drawing these, I'm making sure that everything is an octet and that I'm using the correct number of electrons, which should be 16 electrons for all of these. 2, 4, 6, 8, 10, 12, 14, 16, 2, 4, 6, 8, 10, 12, 14, 16. Yep. So they're all using 16 electrons, and we can use formal charges to talk about which of these 3 structures is the most correct version. Yes, that's a really good question, Ian. For binary compounds, for the ones that are just 2 atoms, those little molecules, like oxygen double bound to itself, yeah, there's really no central atom. And also, because they're the same element, they're assumed to have the exact same kind of bonding pattern and formal charges and things like that. Yeah, so it's not really a central one. Yeah, good question. There's actually not even really geometry. We wouldn't really talk about molecular geometry until there's at least 3 atoms. And that's kind of one of the questions on your assignment is, when do you start talking about geometry And that's typically when you have three atoms. And so there's some sort of pivot point in the middle where you figure out exactly what bond angle that pivot point's at. Really good question. All right, let's take a 5-minute break. We'll be back here at, what I brought us to 2:07. Let's say 2:12. Start funneling back in at 2:12, and we'll have some fun. If you want to hang out and ask questions, I'll be here. Take a quick 5-minute. Oh, you got a green screen. Yeah, that's a good question, Ian. We're going to talk about hybridization next. It's going to make this bonding stuff really weird. So I'm going to start by posing a dilemma. And when we are looking at an atom and it's getting ready to bond, let's say it has, let's just talk about types of electrons. Let's say it has 6 valence electrons. And I'm just drawing it out. Actually, is this thing going to be helpful? There we go. Yeah, okay. So let's say we have an oxygen atom with 6 valence electrons. And we're talking about these valence electrons in terms of s and p orbital notation. So let's say that these are 2 s electrons, and here's a 2px orbital and a 2py orbital. And this is an oxygen atom getting ready to bond. When we are combining this with another atom on the side, let's say we have a hydrogen atom and it has its 1s orbital, and here's another hydrogen atom with its 1s orbital, and these orbitals are overlapping. Are these hydrogen atoms attacking the p orbitals, or is the hydrogen atom going after the s orbitals? Because those are slightly different energies and could produce different results. And so how do these orbitals prepare for bonding? And because of this kind of dilemma or this question that appeared, and we're going to dissect this question a little bit more, is we have an updated version on understanding bonding orbitals and these lone pair orbitals, and it's called hybridization. And so this is another way to look at like a deeper level of looking at bonding. When you're just drawing this line between oxygen and hydrogen, what is actually happening with those electrons? What is happening with these lone pairs that are stuck on the side? Where are they? And so I'll talk about some evidence of why hybridization is considered, why the theory is popular, what evidence supports this, and then ultimately we're going to talk about identifying hybridization of bonding orbitals and non-bonding orbitals. So we're going to do that right now. As far as notes go, there are some models that we're going to try and draw. So it's going to be a bit of drawing. This is kind of the fun part. I do want to keep in mind that we're only spending 30 minutes doing this. So I have a lot of this stuff prepared. I didn't make the images on here. I actually borrowed this PowerPoint from another source and I modified it just because there's some good images on this one. So, and I of course changed it to fit our class. But some things that we're going to get through on hybridization is valence bond theory and orbital hybridization. We're going to talk about overlapping orbitals and what this means for the covalent bond. And then towards the end, we'll get back into resonance and delocalized electrons, or electron delocalization. And that gets into, we probably won't get to that today just based on the pace of it, and that's fine because this PowerPoint's already available to you on the stream, so you can preview it if you want. The resonance and electron delocalization is a really interesting concept. And for your assignment over the weekend, we don't need to know about it yet. So I do want to introduce the hybridization part though, because it's the molecular orbital stuff that you're doing over the weekend is usually done first, but because we have some experience with at least seeing the geometries, I'm okay talking about hybridization because I think it'll actually help out with our geometry work over the weekend. And I'm going to bounce back and forth between this and our visual from, actually I'm going to share not just the document screen. I'm going to be bouncing between this and our molecule program. There we go. So valence bond theory, again, there's a lot of text and I tried to cut out some of it, but I want to identify the main parts that are important. With valence bond theory, basically when orbitals overlap, the electrons occupy the overlap region. This is kind of the definition of a bond, overlapping orbitals. Now, the predicament of whether they're s orbitals or p orbitals, we'll get into that. But a bond is just overlapping orbitals, shared space, where in that overlapping space, there's still only a maximum of 2 electrons And these electrons must have opposite spin pairs. So still, it's kind of like that box model. If we're talking about an that's still a highlighter. 1 second. If we're talking about an oxygen-hydrogen bond, that line between them, we can still represent it as a box model. We're saying there's 2 electrons being shared, and that is one spinning up and one spinning down. And as far as what box is that, what orbital is that, what is that bonding, that shared bonding orbital, we're going to call it a hybridized orbital very soon. And so it still follows the up-down spin rules, 2 being shared. If we draw an extra line for a double bond, which I know that wouldn't be oxygen, let's say change it to hydrogen, we'd have another box, one for one line and one for the other line, and we're going to identify which ones are which. So just overlapping orbitals are sharing electrons and still follow some of the maximum 2 rules. The greater the overlap, the stronger the bond. I think I'm going to have a better way to explain that, but essentially, if you have double bonds or triple bonds, there's more overlap going between the elements, and so more electrons being shared leads to a stronger bond. And I have another slide that kind of emphasizes that as well. So again, you can just paraphrase where you can and abbreviate, and these are your notes. I'm not grading your notes, but it's good to have this information down as a baseline. So if I were on your end, I would write down valence bond theory, covalent bonds when 2 atoms overlap, pair of electrons occupy the overlap region. Overlapping orbitals accommodate maximum 2 electrons, and they must have opposite spins. So that's kind of how I'd cut out a lot of those filler words. Greater the overlap, stronger the bond. And when I'm taking notes, I'll often, instead of doing the, sort of like, I just draw a little arrow. So the greater the overlap leads to stronger bond. So hopefully that wasn't too obnoxious. Let's go on to the next slide. Let's take a look at this, some of the visuals. So these are bubble models. These are electron density models where the bubble is showing where the electron is most likely to be, and the arrows are showing electrons. So when they overlap and there's 1 electron from each being shared, the spin states have to be opposite. There's additional space. You can see the bubble model. There's still a lot of space where they're not overlapping. And we used to talk about molecular orbitals, molecular orbital theory, which is a very detailed look at what's going on here. And there's like bonding orbitals versus anti-bonding, which is this kind of this word that freaked everyone out when they're learning about those. We don't have to do molecular orbital theory anymore, thankfully. So we'll just say these are where the electrons are being shared, that's bonding locations, and this is now where the electron's not likely to be because they're not in bonding orbitals. So that's an overly detailed look. Basically, there's overlapping orbitals. That's what we get from this image. And these bubble models are helpful. I'm going to go ahead and move forward. Some of this stuff's just nice to look at. You don't necessarily have to write everything down. So when we're looking at 2 atoms, hydrogen doesn't really have any options. Hydrogen only has an s orbital. So hydrogen is really kind of immune to hybridization. And this even here isn't entirely correct because it's showing overlapping of p orbitals, but even in fluorine, there's some hybridization going on, so it's not entirely correct. Not using hybrid model. So that for that top right one, it's not following the hybrid model. We'll see how we can adjust that in just a moment. But a little bit of a list that I made for us. This would be a good thing to write down. When we're comparing bond strengths or different elements and how strong the bonds are, the distance between the atoms is pretty important. So if we have fluorine gas, F2, versus Br2, those are both single bonds. They're both halogens. Which would you assume to have a stronger bond energy? Well, we can talk about size. Often size affects the energy required to get these particles away from each other. Even though bromine has a lot more electrons and protons, the fluorine atoms can get really close together. So we'd say that the fluorine bond, fluorine-fluorine bond, could be stronger than the bromine-bromine bond based on their difference in distance. If I draw relative sizes, here's fluorine versus bromine, and we can look at these lines represent the internuclear distance, and the distance between particles is very important for Coulombic forces. So we can say the F2 bond is stronger than the B2 bond, even though Br2 has a lot more protons and electrons. Okay. And that's just the energy required to get those atoms to, that bond between those atoms to break. So this is one that you might, I wouldn't necessarily try and write down everything. I would just, let's just read this one together and consider it. And if you want to write this one down later, you can. But basically the situation is, if we have a carbon atom, and we know carbon atoms have S electrons and a couple P electrons, what happens with these electrons? Which ones go to which hydrogen? When we look at hydrogen and we look at their orbital diagram, each hydrogen comes equipped with one S electron. Does this go here or does this go here? Which of these electrons does it grab, an S or a P? And if it's grabbing an S, one hydrogen is grabbing an S orbital and the other hydrogen is grabbing a P orbital, are those bond lengths going to be different because they're different overlapping orbitals? So are the four bonds different based on the orbital the electrons are in? And so we can consider this question, and this should help us understand bonding a little bit better. When we look at the evidence, or what was observed, all right, this is bugging me. So here's an observation. The four bonds between carbon and hydrogen and methane, the basic carbon-hydrogen structure, are all equivalent in length and strength. So when we draw the compound like this, all four of these bonds are the same length and strength, which conflicts with our idea that p orbitals are slightly different than s orbitals. So how does this work? And we can use more complicated examples than CH4 and come up with the same kind of conclusion, where the bond lengths and strengths are the same. In fact, one of the interesting things that we'll get into is the idea between resonance. To give you an overly complicated example, because we can draw this different ways, I'm not going to do the dots for the second one, but because the double bond can be on one side or the other, the interesting thing that happens with resonance structures is that these bonds are all the same length. We can draw with a double bond here or a single bond here, or a single bond here or a double bond here, but both of these are the same length and strength, even though one is technically drawn as a single and one is a double when we draw it out. But in reality, these are the same length. So resonance proposes a really interesting situation. So we'll come back to this idea of equivalent length and strength when we get to resonance, and that's the more complicated situation. The simple situation is is in a methane, where they all obviously look like the same carbon-hydrogen bond. So what does this mean? And this gives rise to our hybridization. And this is why hybridization is so popular now. It's, again, just a model. So there are ways that this is not entirely correct. There are exceptions that other models maybe explain better. But all we're trying to do in chemistry is provide visual models and ways to easily understand complicated situations. So here's the hybridization model. Orbitals that exist during bonding are not the same orbitals that exist with the individual atom. So they're no longer s orbitals by themselves. They're no longer p orbitals by themselves. They hybridize into new orbitals when bonding occurs. So again, this is a wall of text, but let's, orbitals from bonding are different. Bonding orbitals are different than atomic orbitals. So we can now reference bonding orbitals versus atomic orbitals. Atomic orbitals are individual atoms by themselves. That is not a line. And so the individual atoms have the 2s2, 2p6 donation if we're looking at valence electrons for carbon, for example. Whereas bonding orbitals are different. Bonding orbitals are hybridized. So bonding occurs to form hybridized orbitals. And we're going to use molecular geometry, our understanding of what it looks like in three-dimensional space, to coincide with the hybridization model. So to jump to this really quick, and then I'll jump back to the slide in a second. If we set up methane, here's methane, it's assumed that all four of these bonds are going to be the same in methane. And if we set up a three-dimensional flat structure like boron trifluoride, let's say we have boron trifluoride, all three of these bonds are going to be the same length and strength. These are hybridized bonds, and we're going to try and explain what these look like. So the number of hybrid orbitals formed equals the number of electron domains for an atom. Number of hybrid orbitals formed equals the number of electron domains for the atom. I would just write that whole thing out. And what are electron domains? Electron domains include bonding domains and non-bonding domains. This chart is for you just to look at maybe later. Don't copy this whole chart down. We can reference it. But we have a notation for hybridized orbitals that we'll get to. But for now, those two statements at the top are the ones to write down. Don't just look at the chart. And a domain, the way that I commonly think of a domain is a direction off of the central atom where electrons are. So the key to hybridization is counting how many electron domains you see. How many directions are coming off this central atom. That's the key. And so this is just a strategy I can show. And so the concept of hybridization is relatively complex. The actual practice of identifying hybridization type is really straightforward when you know what to look for. So I'm going to overcomplicate a really simple idea, is what I'm going to try and do, because it's worth the explanation, but in practice what we actually have to do is very simplified. But I like hybridization. I love talking about this stuff, so I'm going to overcomplicate it a little bit. And we'll overcomplicate it with some images like this. So let's look at what hybridization is actually doing. If we take the carbon atom, and this section right here is worth drawing, because we're taking the atom, the atomic orbital, the individual carbon atom, and as it prepares for hybridization, what happens is it actually blends s and p orbitals together. And so the orbitals fuse into a new orbital where all three the same type. And if I drew an s orbital separate and a p orbital separate, what we're getting are called sp orbitals. In this case, sp3 orbitals, and I'll talk about that 3 in a second. If I draw an sp3 orbital, it looks like one side looks like a p orbital and the other side looks like a little s orbital. It's like a little bowling pin. So a hybridized orbital physically looks like a blend of s and p orbitals if you're trying to draw it. You won't have to draw these from scratch on an AP test, but it's nice to see what they look like. So this is why all directional bonds off of carbon are the same, is because the s and p orbitals hybridize to support 4 directions. So all 4 of those bonding directions are the same orbital. The 3 comes from how many p orbitals are involved in the hybridization. So there's a total of 4 domains. We talked about electron domains, 4 directions. 1, 2, 3, 4. 4 domains, it needs 4 hybridized orbitals where they're all the same. So to get 4 domains, it takes one of them from an s orbital. I don't know if you can see my... I'm not even screen sharing. I'm not even... Oh my gosh. You guys aren't even looking at this, are you?
I can see it.
Oh, you could? Okay. I looked down, it says not screen sharing. And I was like, I'm just talking to my face. Okay. So 4 domains. They're all the same. And so the idea of getting 4 domains being the same, you take 1, 2, 3, you take all 4 of these, blend these together, blend that together is an s and 3 p orbitals. S and 3 p orbitals. That's where the sp3 notation comes from. And so if you count the exponents, there's technically a little 1 in front of there, just count the exponents. 1 and 3 add up to 4. I love the math that we're doing right now. 1 and 3 add up to 4 domains. S and 3p. So we can do a little finger math here. But you can see the localized electron model. This is a localized electron model. This bubble model shows the overlapping space. The hydrogens are still 1s orbitals, but the carbon orbitals hybridize to support 4 equal bonding directions. And so this is the orbital diagram that we use. Now check this out. How does this work? Well, each of these boxes have one electron spread out. That's the 4 valence electrons for carbon. Each of these is a valence electron. These each represent a valence electron of carbon. They're spread out, one in each, ready to accept an electron from hydrogen. So each of these hydrogens come in with their 1s orbital and fills up the space. And so when carbon bonds with each of these hydrogens, it now has a full octet because it's filling up their bonding orbitals. It's leaving some room. Now this is not, this example will, what I'm doing right here will help with other examples where there's lone pairs. It gets a little more interesting when you see the lone pairs. Am I moving at an okay speed? Can I go to my next picture? Try your best with drawing this. It's like if I were drawing this from scratch, I'm trying to draw some 3 dimensions. So not a perfect cross, not a perfect T, but kind of oval shaped. The hydrogens, I would just draw hydrogens overlapping like this. So if I was drawing this localized electron model, I'd kind of do it like that. And then I'd notate this as an sp3 orbital. Each of those carbon orbitals are sp3 hybridized orbitals. All right, I'm using up a lot of our time. This one's interesting, check this out. So this is for ammonia, and we know that ammonia has a lone pair on it. If I draw the Lewis structure, it has a lone pair on it. So how does this accommodate for lone pairs? Those are hybridized orbitals as well. Lone pairs are hybridized orbitals. Lone pair are still hybridized. So the lone pairs exist in the same type of orbitals as the bonding orbitals. So when I look at just the Lewis structure for in the top right corner, there's still 4 domains coming off of it. 1, 2, 3 bonding domains, and a 4th non-bonding domain. So lone pairs count as an electron domain. 4 domains, sp3 hybridization. 4 domains will always be sp3 hybridized, which is pretty cool. That's the actual, that's the way that this is simplified. Count the domains, that has a direct correlation to the type of hybridization. 4 domains will always be sp3 hybridized. And you can see, because nitrogen has 5 valence electrons, that there's only 3 hybridized orbitals that can bond, and one of those is already filled up with the 2 arrows, and that's a lone pair. And I kind of hinted this earlier, and someone answered me in chat. This was a couple days ago, a couple lessons ago, but I said, why do you think we call them lone pairs? Why do we always draw the dots in pairs? Because those dots are existing in hybridized orbitals, and they stick together. One's going up, one's going down, but they're physically a pair. They're filled up hybridized orbital that's not bonding, so non-bonding electrons. And your task this weekend is to explore the geometry. So this one's called a trigonal pyramidal geometry. And that's fun. So I'm going to show just visually, don't worry about writing because I want to get you out of here. Here's water. You can go check this out. The PowerPoint's already up there. But this is a 3 domain. If it's only 3 domains, then it's only sp2 hybridized. It only needs to hybridize 3 orbitals for 3 domains. So one of them is an s orbital, and the other 2 are p orbitals, sp2. It's physically, it's just the exponents are just counting how many orbitals are involved. And there's an unhybridized, one of those p orbitals is called unhybridized. So it's an empty p orbital. And this is what happens when you get down to 3 domains and 2 domains. So again, I'm going to backtrack a little bit on Monday, and we're going to keep talking about this. So these slides, I'm just kind of showing you to give you a more complete look before I excuse you. But I'm going to backtrack, and we'll actually talk about these in more detail. Here's a cool little orbital model where all the colored sections are hybridized orbitals. And you can see this little p orbital that's still shaped like a normal p orbital because it's not hybridized, unhybridized. And this is sp hybridization, where it's only for 2 domains. And this is what happens when you have those triple bonds between nitrogen. It's sp hybridized, for example. It only needs 2 orbitals, and you have remaining unhybridized. These unhybridized orbitals are what happens when there's double and triple bonding. So anytime there is double and triple bonding, it has to do with interactions between these unhybridized orbitals. And that's a conversation more for Monday. But I love this stuff because you get some great visuals once you get used to reading these. And here's an example of what these hybridized orbitals can look like. More bubble models. We'll get past 4 domains. If you get up to 5 domains and 6 domains, here's where they have expanded octets. So this is phosphorus that has 10 electrons through sharing instead of just 8. And here's some really complicated hybridizations for up to 6 domain geometries that you're going to explore over the weekend. So you'll look at these geometries over the weekend, and we can come back and explain it through hybridization. You can see that the d orbital is getting involved to accommodate for an expanded octet. So what you're mainly going to be doing this weekend is exploring geometries and looking at bonding and non-bonding domains. And I want to pull up I know we're at 45, just bear with me for a few minutes. You're not going anywhere anyway. So let's pull up the assignment for the weekend. And I'm not trying to belittle your time. I know your time's useful, but this is important. So I'm just gonna pull this up from scratch. I posted a lab assignment. I'm calling this a lab because we're doing a simulation using the PhET simulation. There's 2 simulations you're going to use in this lab. So I put up the molecule shapes one, which is the more advanced one that we were looking at. And then we have the polarity one, which is the second half of this. This is largely a you figure it out lab using the simulations to discover patterns. So for the polarity one, 2 atoms, 3 atoms, real molecules, you get to move these around and adjust their positioning. And this one has to do with difference in electronegativities. This stuff on the right side, just see what happens when you click them. The instructions are pretty clear on how to set this up. And you can see how this molecule responds to an electrical field based on geometry and differences in electronegativity. So that is where you'll get to when you go through this series of steps. And the lab has instructions that'll walk you through these simulations very specifically. And so when you get to this point, it's more manageable. So here's the lab. And I made a copy for everyone. So each of you have your own version of this. If you want to fill this out on Kami, you can. And what I did is I went through and I highlighted the sections that you're actually doing. So you can see a little highlight here. As far as your response, what you're turning in for the lab, you're completing all the highlighted sections. The rest of this are instructions and guidelines. So I'd read through it. Part of doing the lab is actually reading this stuff. This is an activity I've done pretty much every year I've taught AP Chem, so it's great. Sketching the Lewis structure. If this is not enough space, just do it on a separate piece of paper. I think it'd be easier if you're doing it on a separate sheet of paper, so you don't have to try and fit everything in here. Just label which section you're working on. Table 1, draw this table. And then here's an explanation. More explanation. This asks you to hop on and use the simulation for the molecule shapes, which is a link on the classroom section. Again, use that to fill out this table. This is going to look pretty similar to the assignment we just did, by the way. This table. And then here is the expanded table that I kind of started showing you, but then I reverted and said you're going to do this anyway. Table 3 has you naming electron geometries and then molecular geometries. So finish the table. And again, if you're doing this on Kami, it's nice because this table is already kind of filled out for you. And then you got to be careful because little questions, you got to answer these questions. So I highlighted each of the questions. I labeled them A, B, C, D, tables, questions. So just look for the highlights, and those are what you are doing for this lab, whether it's on Kami and you're filling this out, or you're doing this on a separate sheet of paper. You're filling out this table and filling out this table. So it's 12 pages, but most of it is just reading and models. Like several of these, you're not even answering stuff, you're just reading it. So that's your assignment over the weekend. I set it up to be due on Monday, but by the end of the day. So if you don't have it finished by the time we come back on Monday, you still have some time to ask questions, and we'll follow up on hybridization. We'll even get into geometries and polarity in class on Monday. But the idea behind this lab and why it's really important to do this before you come to class on Monday is you're getting exposure to this information. You're trying it out before you come in and ask questions. So you get to kind of figure out the patterns on your own, and then we'll explain them further in class.